forefront to have climate change in the future. Australia happens to be in a hotspot with these augmentations when they become available. You're going to see sufficient satellites to get really good positioning, even in the middle of high-rise CBDs.
We hope to be able to deliver a product that will enable users to position their mobile phones to around 2 centimetres. So we're taking its scientific infrastructure and making it available to the general public.
The ability for people to access remote sensing product through their mobile phone has effectively transformed expectations from the public about the access to environmental information from remote sensing.
We track GNSS satellites, we track remote sensing satellites, bring data back from remote observatories, including observatories in the South Pacific and Antarctica, then goes to the international community where it's used for a whole range of things.
We have a growing archive of over 30 years.
30 years ago it was a difficult task to process one satellite image. Now we can process tens of thousands in a day potentially.
And with the launch of Landsat 8 now, we've got a continuation of that.
I can look at one spot and I can say, find the water and go all the way back through time. And I can do it for all of Australia in one go. We've taken all of our imagery right through our entire archive and we've made them available in a constant, accessible way.
In future, I think it would be really exciting to integrate new satellite sensors and to use methods of data interoperability to look at the landscape in new ways.
Now that we're actually working in a supercomputing environment, we're enabled to include other agencies all around the world in collaborative environments. That means a lot more accessibility to data, a lot faster outputs, and a lot broader impact of what we do.
In the next 5 years or so, there are going to be some amazing satellites.
It used to be the domain of scientists and technical specialists only to make use of this information, but the combination of satellite remote sensing and high-performance computing is transforming our ability to make use of the information that we collect from satellites.
Well, ladies and gentlemen, welcome back to the rest of our plenary session. That marvellous piece of open was developed by Geoscience Australia, and it gives us a lovely snapshot of some of the most significant activities that our premier national geoscience organisation is undertaking on behalf of Australia. And that's a very nice lead-in to our first speaker, because our first speaker is Dr. Chris Pigram, who is the Chief Executive Officer of Geoscience Australia. Chris has been a leader of remote sensing thinking inside GA and of course nationally. He's helped the organisation develop some very significant national initiatives over a number of years, and he's going to tell us about those and others right now. Would you join me in welcoming Chris to the podium?
Good morning, ladies and gentlemen, and thank you, Peter. Thank you very much for that introduction. What I'd like to do this morning is tell you a little bit about the agency and then focus in on some of the very interesting developments that we have underway in the remote sensing space, and some of those were previewed in that movie that you just watched. So, this is the areas in which we work, and I'm not going to cover all of these topics this morning, but I'll skim through some of them very quickly. If you take the broadest interpretation of remote sensing, we do a lot of geophysical remote sensing, and that's very much a vital part of the activities we undertake, as well as some of the more traditional remote sensing that we've indicated there on the right-hand side of the slide. Oops. So let me just keep going. So one of the big areas that we're involved in that is very much a focus for the nation is energy. And as many of you will know, Australia currently has quite extensive gas resources. And these are being developed to feed the demand for energy and different types of low carbon energy in our neighbours to the north and to the west. But in the process of doing so, there are a range of other social and issues that have arisen around the development of some of these areas. And that brings us into play around a whole range of issues, including groundwater developments and the impact on groundwater, as well as understanding, using remote sensing techniques, whether or not there are any particular impacts in the environment. Community safety is another theme that we're very focused on, and this has to do with all of the natural hazards that might occur. And we have a role in assisting the community to respond to, or anticipate and respond to all of these potential events. Flooding in Queensland recently, in the last couple of years, which have been rather wet, were thought to cost something like $5.6 billion in federal government assistance in rebuilding. So it's very much trying to better understand what's happening in that environment is a significant role that we have as well. I briefly mentioned groundwater, and groundwater is fundamental in a country as large as this and as dry as Australia. And it's a vital resource for a whole range of reasons. It provides about 1/3 of the water consumed in this country. It's the only source of water for many regional and indigenous communities. It's essential to many mining operations that underpin our national economy. And it's often vital for agriculture and towns during dry periods or during droughts. So we use remote sensing in a whole range of ways to understand our groundwater resources, and these vary from understanding groundwater-dependent ecosystems through to using LiDAR to understand some of the very young tectonics that control some of the recharge points in a lot of our groundwater systems, for example. In the environmental space, we have a whole range of activities, but what I've chosen to illustrate here is some work that we did a few years ago where we produced the first ever seabed classification system as part of a bioregionalisation process. And this has been based on extensive multi-beam work where we're mapping the benthic environment and using geoscience or geological surrogates to understand what the benthic ecology might be. This has been a very important input to our marine planning and for marine protected areas. In addition, the map here on your left, which shows Australia's jurisdiction, and is missing a couple of islands, but basically this jurisdiction has been defined on geological parameters around seabed mapping under the UN Convention of the Law of the Sea. So in addition to knowing where our boundaries are, we're also heavily engaged in the region as a consequence of our partnership with the Australian Aid Agency, AUSAID, and we are passing on the skills for mapping the boundaries to our colleagues in our Pacific Island nations, for example. But we also are involved in disaster risk reduction programs around the region, where we have people based in Indonesia currently, but we're also working with the Philippines and Papua New Guinea, and those countries experience all of the natural hazards that you could experience, including volcanoes, tsunamis, landslides, earthquakes, tropical storms, floods, and volcanic eruptions. In relation to the resources sector in Australia, one of the questions we get asked all the time, and remote sensing is actually going to be a vital part of answering that question, is Australia mature for minerals exploration? So this map is a geological surface map of the country, and all of the yellow and green areas that you see there are areas where you won't see rocks in outcrop, where you won't be able to actually go and kick a rock. So you can see a very large part of the country is covered. If I now show you a map which shows what we call the solid geology of the country, this is areas where you might see some outcrop, and I impose on that all of the current major mineral deposits. You can see that there's a very strong correlation between where the major mineral deposits occur and where you can find outcropping or near surface geology. But if I now add to it an aeromagnetic underlay, and if you're not aware of what this is magnetic data, so the rocks have a magnetic susceptibility. We're collecting that with an airborne technique and looking at what lies underneath the surface. Think of this as a geological MRI. You can see in many places there are extensions to those areas of major deposits that go undercover. So under the plains and the red sand that characterise the outback of Australia, there are very extensive areas where the provinces extend, and these are the areas that have potential for future development in terms of identification of major resources. My agency has been tasked with trying to reveal what this basement geology is, and in the process of doing that, what we will attempt to do is exploit these national data sets that we already have and turn them into geological models through inversion to try and develop a testable geological hypothesis for what is under that surface, and then we will drill it to obtain the samples to build a story about what's actually there. So let me turn to remote sensing as you would understand it, senso stricto, and if I can maintain the geological theme for a moment. This is the first ever national ASTA data set that was being produced by our colleagues in partnership with Geoscience Australia, our colleagues at CSIRO, Dr. Tom Cudahy. So what we've done here is pulled together all of the ASTA data that was available to us. So the project involved compiling over 3,500 images and cross-calibrating these with each other and with other hyperspectral images from the Hyperion instrument to produce a single, consistent national map. I should say this data is actually derived from the ASTA instrument on board NASA's Aqua satellite. This one shows iron oxide in our landscape, but there's a whole range of other minerals that one could map, and there's a whole range of questions that you can answer, despite the fact that, as I said previously, we're going to focus in our undercover areas. This work actually has a whole range of applications, not just in mineral exploration, but a whole range of other environmental applications. And it's all available through an online viewer, using the NASA Whirlwind 3D viewer, and you can burrow right down into great detail and find some stuff very locally in terms of what's actually happening in the near surface and what's moving. So it's essentially a chemical map of the surface of the continent. In addition, so turning to a completely new area, thermal remote sensing is used every day to detect and map fires. Australia is highly prone to bushfires or wildfires if you're from North America. And Geoscience Australia operates a Sentinel bushfire hotspot system which operates a continuous feed of hotspot information to fire and emergency services, people in this country, to private companies and to the public. These capabilities are based on a MODIS science instrument on the Aqua and Terra satellites and are taken, as I've said, as an operational capability by many users across Australia. One of the less obvious uses of a map like this is to map national distribution of fires. And it's a sort of analysis that insurance companies will do with the Sentinel data to inform their understanding of fire risk. The video here was produced by the Australian Broadcasting Corporation for a documentary series that ran during 2012. Let me now turn to optical remote sensing. And the great historical achievement here is the continuity of observations thanks to the vision and foresight of William Pecora, who was the director of the USGS in the 1960s. The continuity of observations is important because it allows analysis of time series observations, and provided the observations are geocoded, calibrated and liberated from the archive, it's possible to look at change through time. And I'm going to show you what we're doing in this space. If it will move on. Thank you. But before I go into some of the details, one of the things we needed to do was go back and think through, if we're going to liberate the archive, how do we go about that? So we've been custodians of remote sensing data since 1979, when we started to capture and store the initial Landsat data. This archive holds a treasure trove of information about change through time in our landscape, so our challenge was to how to liberate that information from the data. So we needed to work towards a common platform for the delivery of public good acquisition, standards of acquisition, storage and delivery to meet the different needs and applications of our users. Having acquired the data, it had a geometric correction applied, it was calibrated for atmosphere, illumination and surface reflection asymmetry, which produced a normalised measurement of surface reflectance. We'll have the next one, please. It looks like our little device here is not working. This in turn, having said about acquiring the data and storing it, we realised that we were left with a major challenge to manage a rapidly growing archive and, more importantly, making it accessible and usable. So through a series of corrections and by accessing high-performance computing, we have been able to standardise the images and begin to extract the information required. And I'll illustrate some of the work that we've done in this space shortly. Go to the next one, please. But the end game, of course, is to deliver some value. And the way we've structured this business model, it's almost agnostic of the question that might be asked. If you need to understand what's happening on the surface of the continent, it should be possible to pose the question and we can go back through the archive and deliver an answer for you. So there are many clients, many possible questions, and we're quite confident that we can now, because of some of the work that Adam Lewis and his team have done, that we can provide very well-founded answers to that question. Thank you. So let me show you some of the things that we've done to make this possible. One of the first steps was the production of a geographic reference of known accuracy that can be used to ensure consistent registration of satellite images. The image on the right is the reference image itself, and the image on the left is the accuracy map for that reference image. AGRI, as we call it, was produced from almost 10,000 individual satellite images taken from the JAXA ALOS missions between 2006 and 2010. The production of this product involved innovative technology developed by the CRC for spatial information and is an excellent example of the collaboration that can happen to tackle some of the challenges we face in extracting value from the remote sensing data archive. We now have an image across the entire continent that is mostly better than 5 metre accuracy. That's the yellows and the greens on the imagery. Didn't work. Thank you. Having calibrated the data and developed physics-based methods to do so, to allow for atmospheric and illumination effects, we are now able to produce seamless mosaics, and this is just an example from northwest Victoria and southwest New South Wales. Because, as you can see from this example, there are none of the usual discordant boundaries that you would see in a mosaic of satellite imagery. Next one, please. Can you just go back one? It's just kicked over. Yeah, thank you. And that needs to start. Can you start that movie, please? No, not that one. That's it. Thank you. We've also made major advances in the management of big data sets, producing a multi-temporal data cube, which is illustrated in this slide. The data cube supports analysis of time series observations. To produce the data cube, each image is diced into a time slice series tile stack, which you saw earlier. This allows us to be confident that we're comparing the same piece of the surface of the continent through time. This is vital for the analysis to be usable, reproducible and trusted. So we could move on to the next one. Yeah, thank you. That image of Australia needs to just be allowed to run as a movie. Thank you. Although each Landsat instrument has improved in quality, the impact that optical remote sensing is starting to have, coming from the inclusion of time, frequent observations and long time series. This image is the first national, consistent map of Australia's land cover. It was only possible to make this map by combining many years of data from the MODIS instrument, simply because the surface vegetation changes constantly. To classify the land cover type, you have to have enough observations to capture at least a year of dynamic change. So this allows us to understand a whole range of issues, including changes in agricultural and forestry, for example, the extent of irrigated pastures and the extent of forestry for carbon accounting, changes in wetland, the extent of terrestrial vegetation encroaching on aquatic vegetation informs condition monitoring and management, and the decline and recovery of vegetation through periods of extended drought or extreme trauma like bushfires. So this is just an example of the detail that one can extract having done that data cube work and collected the archive to the extent that we have. So not only can we get a national scale view, we can actually look at a particular region for a particular purpose. And you can see here a range of paddock scale activities in farmlands where we can look at how these paddocks have behaved in an irrigated environment versus a rain-fed environment during a period of time in Australia that was particularly dry. So the graph in the lower left-hand corner shows changes in greenness as recorded by MODIS over several years, and the use of time. This time series allows quantitative descriptions of the cropping patterns. We can also identify periods of fallow bare earth percentages in this process. Doesn't like me. Can I have the next one, please? This is also a movie, if you could run it. Thank you. We can also apply this technique to community safety issues. This is an example of preliminary flood analysis completed last year, which shows the flooding history around the city of Kerrang, which is about 300 kilometres to the northwest of here. In this image, the areas, could you run that again please? The areas that are always water are coloured pink, and the areas that are rarely underwater are blue. It's a very good example of being able to have a close look at where water ends up in the landscape in extreme events like flooding events. And this short historical analysis shows us just how well the city's levee banks have worked during this period of flooding. But the future applications of this are very many, including being able to predict the extent of floods in an environmental flow circumstance, for example. So there are plans in the future to release environmental flows down the river that led to this flooding. That will necessarily mean farmlands being inundated. So simply understanding where the water ends up, who's inundated and who isn't, will be an important part of managing that process. Could I have the next one, please? As Senator Lundy mentioned in her presentation earlier this morning, there's going to be a great deal of work done within the Commonwealth to look at where we need to be in future. So the first, based on a whole series of reports that were derived from a range of sources, we now have two important plans, the Earth Observation from Space Infrastructure Plan and the National Positioning Infrastructure Plan underneath the Australia Satellite Utilisation Policy. Can I have the next one, please? The National Earth Observation Infrastructure Plan is focused on 5 priority areas, and they're listed here. So coordination, continuing the observations, including from commercial sources to ensure the time series is sustained, ground segment and calibration capabilities, extracting information from the data and sustaining the skills and knowledge base. Could I have the next one, please? I'm not going to go through each of those and show what's developed, but as Senator Lundy indicated, in terms of national coordination, here's a range of examples that have allowed us to improve what's happening and get better coordinated nationally in terms of what we're doing in this space. So an Earth Observation Coordination Group has been established. It's open to government, industry and academia, and will assist in keeping all interested groups informed on EOS issues. There will also be a rolling review of Australian Government Earth Observation from Space requirements, which will not only help us, for example, to be clear about what data should be collected, but will assist the commercial providers to understand the needs of the Australian Government. We've become an authorised user of International Charter for Space and Charter on Space and Major Disasters, so that we can assist our first responders in the disaster space to get access to Earth observation from space data more quickly in the event of an emergency. There is CSIRO's leading a major activity to coordinate our CalVal activities across the country so that we do have a coordinated approach to this issue. And we, GA, have signed up an agreement with our partners at ANU for a national computational access to the national computational infrastructure, which is the high performance computing capability, which will allow us to readily process the information that we wish to deliver to. If I can just skip over these next two, I'm about to run out of time, so I won't go through those. So if you can move it on to the next one, please, and the next one. Thank you. So in conclusion, I think I've demonstrated that remote sensing is a vital source of geoscience and scientific data for Australia. The ability of Earth observations from space to provide everything from national to local scale coverage is fundamental to our ability to map and monitor this continent. The use of remote sensing data is only likely to grow and will be vital to the well-being of our society. Progress in the application of remote sensing depends on collaboration and knowledge sharing. The work GA does not stand alone, but is a reflection of the cooperation and teamwork across government, the international community of satellite operators, the research sector and industry. IGARSS is one of the most important forums for these interactions to happen. So thank you for the invitation to talk to you today, and I wish you well with the rest of the conference. Thank you.